I just did something, I guess, for my own amusement. That's really crude. But the code in the presentation, it's up on GitHub at that URL. I guess you just search for TPM _ reinventing the wheel, and you'd find it. So the basic situation I was trying to solve was, if you've got a computer and you're not allowed to mount USB devices, you can't connect onto the local network, and you can't do Bluetooth, and you can't burn media. What if there's some data that you have a need to transfer? So the obvious things whose purpose is transferring data are locked down, but there's often other ways. They're not thinking of things that, it's not the purpose. So you could, display an image on your monitor, capture the image, and do some image processing that convert that into data. You could do some timing some stuff so that you could look at traffic over VPN and just use the volume and timing. Or most computers allow audio. So what I decided to do was the easiest seemed to be audio. Support's built into the OS. I can capture audio with existing utilities. I don't need to do any timing because your sound cards will do all that. I don't need to develop image processing. So what I decided to do was I would code the data into a WAV file, and then I could play the WAV file with a standard media player and hook up to another computer just via an audio cable and record the audio to a WAV file, and then just decode from that recording. So for proof of concept, I try to keep it simple. So I had just use 8-bit audio at 8 kilohertz. With 8-bit data, I don't have to worry about numeric overflow. The file size is probably small enough, and I can inspect things fairly easily. And I don't need high fidelity hardware. So that's all to the good. And so I just chose, okay, let's just have a simple audio pulse with spaces between the pulses, and I'll just count, is there a pulse in the window, or is there not, and give me my ones and zeros. I just chose a pulse that's derived from a sine wave, just because that's probably more natural for audio than like a square wave or something like that. I had to do a little bit of research in terms of what's the format of a WAV file, because when I take the recorded WAV file, I need to be able to interpret it, and it's fairly simple, but it took me a little while searching around to get really the details. So it's the WAV. It's a Microsoft format that's a resource information file format that basically has a tag, and then something says how much data there is, and then there's the various chunks. So for a WAV file, it says it's a RIF file, then it has a tag that says WAV, and there's something that says what the format is. There's something that says what the length of the format is, and there's information what the format is, how many channels, what the sample rate is, and if there's block alignment. It captures that fairly simple, and if I'm looking at 8 bits, it's pretty simple. None of the data is just byte, 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 byte. Following the format, there's just a tag that says data, and something that says how there's a 4-byte unsigned little Indian int that says how much data there is, and then the data just a bunch of bytes. 8-bit data is, they've got the 0 is 128. So an actual 0 is loud, and an actual 255 is loud. And it's, you know, really simple just to write the head for the WAV file. Just pack and print. So for the pulse, I basically just took a sine wave and shaped it with a Gaussian. And so in theory, it looks like that. And in code, I basically just trimmed it so that I've got a 20 byte pulse. Anything else before that or after that, I just zero out. So for a set bit, I just put a pulse. For an unset pulse, I just put, you know, a 0 signal. And then as encoded, I don't know whether you can see this very well, but the point markers are just basically showing how things fit onto the ideal pulse. There's not really, there's only, I think, what, eight points for a single wave. So it's like it's 45, 90, 135, 180, etc. And then as well as the 20 byte pulse, I put lots of separation in it in between, so that I guess basically make it simple, simplify the problem. If I record it, it sort of looks the same. It turned out in this case, and it's not always the case, but in this case the pulse is inverted, so I guess I'm not quite sure. I have seen cases where it is the right way, so I don't know if it's a hardware difference in terms of the sign of the pulse. So I know how to do pulses. I know how to put audio data. I can put a wave header. The only thing is, well, how do I say, hey, this is the data? So basically, to signal the start of the data, I put a marker that's just basically FF. So 8 1 bits, and after that I have something that says, okay, this is how much data there is, and then I just have the ones and zeros, the pulses and the non-pulses. I found initially, if you're playing a wave file, the end of the wave may not get transmitted properly. So I added 4 bytes of 0 to make sure that doesn't happen. Later I increased it to 40. I don't know if that's necessary. I did that for when I bumped things up to 44 kilohertz, which maybe I'll get to later. Oops. So the Perl code to write out the data and the header, it's all pretty simple in Perl. I didn't do it the most efficient way, but it works. It's good enough for a proof of concept. where I had to struggle a bit is, okay, it's easy enough to think about how to write the file, but how to extract the signal out of it. So to decode it, I basically take a look at the wave header, make sure it's as I expect, and then I have to scan to find that FF start marker, figure out the length, decode the data. Even that sounds simple enough. But then, well, how do I detect the pulse? I could look at the 1 kilohertz component of the Fourier series. I could convolute it with the original pulse, or I could just say, well, how much signal there is. What I ended up doing is I took the easiest course, which was just sum the absolute magnitude of the bytes in a chunk, and if it's over some threshold A, then it's a 1. If it's under a threshold, if it's below the threshold, then it's a 0. I guess the first tricky bit is to scan through and find the marker, but once I get that, it should be 80 byte chunks, 20 byte pulse, and 60 bytes of silence. So to find the start, you basically take the unsigned data, make it into ints, and then I take a look at the running sum of 20 bytes, and I take the absolute value, and I just chose some arbitrary threshold for, hey, there's possibly something there, and if there's a section where the running sum stays over that threshold for at least 20 bytes, and then things go under that threshold, then hey, that's possibly the start of the signal. So once I find that, basically then look in more detail, back off a little bit, and look for the maximum of the threshold, and then look at the 20 byte chunk. So you should have something that's over the threshold and then something that's well under the threshold. So I basically used 70% of the maximum is a 1, and below 40% is a 0, and anything in between probably indicates I got just too much noise or something's wrong. And then FF would look like those 1s and 0s. And if I don't match that, well, continue on and keep on scanning through the file. So when I'm decoding it, I basically decode 1 bit at a time. That's different from the start marker. I use what the maximum running sum is to base the threshold on, and so I remember, okay, if 20 bytes are over 70% of that, then it's a 1, and if it's below 40, it's a 0, and then verify that the gap in between is all below that threshold. And if I find something in between, give up. And when I've got 8 bits, I get a byte, and just continue until I hit the length. And does it work? Yes, it works. If the file is small. If the file gets larger, I get the signal starts to shift a bit. And if I look at it in detail, I find it's not like drop bytes. It looks like there's a regular shift. The bigger the file, the more the shift. So to compensate it, I basically set a trigger. You know, every I don't know, 20 bytes of decoded data to recheck to see if I need to tune where the starting spot is. So it's basically after like 1.6 seconds of audio. The total amount of shift isn't very big. Like on a 3 megabyte audio file, by the time I get to the end of the signal, I've only had to correct 127 bytes. And do we want a live demonstration? Well, not yet. I don't know if we're going to have one at all, because I think it'd be problematic over live stream. I'd probably muck up the audio and then I'd be silent and you wouldn't be able to hear anything.
Oh.
But before the purported live demo, so what have I got? I got a whopping 100 bits per second. I could double that by to 200 bits a second if I add a second channel. I might be able to use different amplitudes of the pulse to get more than one bit into a pulse. I could reduce the width of the pulse, the width of the padding. I could try to go greater than 8 kilohertz. The code is bad. It's up there at GitHub, but it's bad at the moment. I didn't do it the right way. I didn't start off doing it the right way. I started, well, let's play around and see if this is a viable idea. Oh, and I basically gzip the files before encoding it, so that way on the receiving end, the gzip has a built-in checksum, at least tell me if it's gotten corrupted transmission. It'd be nice to see if I can eliminate the audio cable. I suspect I can if I have a really silent room. Can also use the sign of the signal for more information. I should try different pulse shapes. I could use the shift of the pulse to pack more information. If I examine the data, I could probably determine how much how much things are shifting to see what the frequency mismatch is, and just autocorrect. And second channel, if I had 2 channels, I could have 2 pulses and use the offset between them as well, maybe to get more information. So, if I take the recorded data, this is sort of what it looks like, and you can see this like a regular pattern in that running sum. So the top in the purple, I assume it comes through okay, is the running sum, and the axis is basically the offset in the file. The bit on the bottom is the running sum of those pad bytes. And you can see it starts ramping up, and what this is the correction is hit in there at where it's ramped up. This is like it shifted 3 whole bytes, and I correct it, and then after a while I need to correct it again. But at least it looks like it's not noise that's causing the problem, and it's not drop bytes. It's really regular. And also look at the variation in the size of this signal. So it looks like maybe I've got one part in 4, so I could maybe fit a couple other 2-3 other values in that window. I had when I'm recording and transmitting, I have to sort of be careful in terms of it's like the old audio thing. If you're recording something, you need to match your output and input volumes, otherwise you get distortion. So I did one example that's a lower volume signal, and I start getting it's looking a little bit more sketchy. And the spread is still about the same amount. What was it? 14%, 15%. if I if I take away the resync or make it really, really loose, you can see why things would fail for larger file size. The signal starts drifting into the pad bits, and there's less and less signal until eventually, I can't really determine anything at all. And with the lucid resync, you can see things spreading out. So what have I done? I've reinvented a soft modem, but without any two-way communication, poor use of bandwidth. But so here's the live demonstration. I assume I'm not going to try to do a live demonstration. I guess maybe if I set up another computer and put it in front of the screen, in front of my laptop, we could do something that way. But so what I've done is I basically captured what I would have done. So on GitHub, there's a folder samples which has the sample text and the encoded sample wave. So the text is pretty small. It's about 20 bytes, and put it in a wave. It sort of uncompresses it by, what's that, factor of 700?
About that.
So I'll play the wave file out of one computer and record it on another. Or in this case, I think I was basically recording to myself. And I cut off a lot of the diagnostics or whatever, but yay, it seems that it got something. And if I look at what the output is, I got the original text. So,
are you able to play the wave file for us?
I could. I'm just not sure how things will connect together. Do you want me to try?
Sure, give it a shot.
I need to make sure I play it with the right layer of software.
Yeah, I just figure if it's a wave file, you should be able to just play it using Audacity or something.
I would do it straight to the command line, but I'm not sure which. I know the command line that I was using for in the live demonstration was an ALSA driver, and I don't think it goes up to the pulse audio correctly.
I'm just trying to figure out if that's background noise, if I'm actually hearing the wave file.
Not yet. I'm sorry. I'm looking for the wave file. Where did I put it?
Okay.
Why isn't that? Why isn't where it's? Sorry, it's not where it's supposed to be. Oh, there it is. Askabetical. So I don't know if you can hear that Geiger counter.
That's what I'm hearing.
So did you hear anything?
Yeah, I hear beeping at about a 1 second, less than 1 second frequency.
Okay, that's not right. Let's try another way.
Whoa! Okay. Yeah.
So I don't know. Did you hear that?
Yeah, I did. I did. I imagine the rest of the meeting did. So I'm curious, how did you did you use the speaker on the source system and record it to your phone and then play that recording back later, or did you actually have a cable between two computers, audio cable?
Um, in this case, I took an audio cable from the microphone to the headphone. But I've
Yeah.
also done it between different computers as well.
Okay, so you had an actual hardwired connection then.
Yep.
Oh, okay.
Yeah, so in GitHub, the sample has the original, and then there's a TEP folder which has the as recorded and as decoded files.
That's very neat.
So here's some of the docs I found for figuring out how to do a WAV file. And there's some extras since I was supposed to do this talk 2 months ago.
Yeah, there were complications. And go ahead, our second presenter's not here yet.
Okay, so I bumped up the rate to 44 100 hertz, which is sort of your standard CD
Yeah.
Wave sampling frequency. Let the pulse the same shape and the same size, and just said, oh, well, this worked. All I needed to do was change the wave file, change the number of the sample frequency and the average sample frequency. And there's not really much change on the decoding side either. And it worked. I found with the 44 100, which is probably a more natural sampling rate on my sound card, going from the computer to itself, I didn't see any signal drift. But when I go to a different computer, I still see some drift. And I guess that makes sense. I mean, you're not going to have scientific level precision in terms of, what the clock is on your sound card. They're all going to be off a little bit. And if you look at, it's like 100 bytes out of a million, that's still pretty good.
Yeah.
I also took a look in terms of, if I do a Fourier series of that 20-bit pulse, can I get something that's more stable? If the signal drifts around a little bit, the magnitude will basically shift from the sine to the cosine, and so that the root mean square of the sine and the cosine may give us something that's more constant. And this, unfortunately, I don't think we can really see all of the parts of it, but you can see, okay, I still have that regular sort of defect in the running sum, but the second line, which is sort of an orange color, is really quite stable, which is, promising in terms of packing more information into a single pulse. Unfortunately, I really needed to redo this and force GNU Plot to choose some more user-friendly colors. There's a yellow sawtooth you can see.
Yeah.
Well, I can barely see. That's basically taking a look at the angle between the sine and the cosine components. And it's basically as it's shifting one bit, it's a regular drift in the phase. It's in this case it looks pretty perfect. And if I put those if I put those into a histogram, you can see that the root mean square is really a nice tight signal. So it's 1 or 2%, which means I can probably pack a lot more information into a pulse if I decode it this way.
Yeah.
And that's the end.
Great. Okay. Well,
I got a story to say. Yeah, clap, clap.
as we loses a little when we're not in the same room, but there you go.
A million years ago, probably somewhere around 1978. I don't know if you're familiar with the name, but a fellow that was into electronic music, Isao Tomita. No?
Yes, I think so.
Okay.
I think somewhere I may have like a quarter-inch cassette tape, something from him.
I can't remember the album. I'd have to go into the back room to find it somewhere. But on one of them, he decided to encode about a 1.5 second blip of data into the middle of the song. And on the album cover, he actually mentioned that this piece of information was in there and that you could decode it and decipher the secret message.
The secret message. I love it.
The secret message that was encoded in the album. And it turns out, and it was mentioned in the album, that this was done via the Tarbell cassette interface. Now, I'm dating myself. That was an interface for your S100 computer.
Oh, S100. Yeah.
Yeah, and I had one. And the trouble was, I tried playing the sound back, but it was so short. It was only about 1.5 seconds long. And I believe his interface was either off or the post-production messed up the signal. So I couldn't play it back into my Tarbell interface and decode it using the regular software. And signal was so short that I couldn't retune my card for his frequency. So I ended up writing some software. In the beginning, though, I didn't know what the heck I was doing. So thank goodness for fanfold paper. I got a large piece of fanfold paper, digitized the sound using my Chromemco analog to digital to analog card, and plotted it out manually. Then I looked at what the signal was and figured out, I think I had to measure the time between zero crossings, taking into account a variable DC offset that was going on.
Yeah.
Looking at the distances between zero crossings, I could turn that back into a bit stream, look for the sync pattern, and then start counting out the bytes and decoding the bytes back into ASCII. So over the course of a weekend, the digitizing was done in assembler and everything else was done in BASIC, even though it took forever to decode the software. I eventually did get the message. And it was something about a meteor has crashed into, and I can never pronounce the name, Tunguska, Russia.
Oh,
that one.
That one.
The famous one.
Yeah.
The beginning of the 20th century?
19 something or other.
Yeah. I think it like flattened an area of forest. It was 100 acres or something like that.
Oh, I think it was bigger than that.
Oh, okay. Yeah.
But yeah, that was the nature of the message. So that was 42 years ago that I did this decoding. And if you want to look it up on the web, I just did while you were talking there, and search for Tarbell specification. You can find out about it. There's the circuit board, the parts list, and theory of operation and stuff like that.
Mhm.
And it was encoding, I believe, 520 bytes per second. So it was pretty good.
Pretty good. Well, I can remember using the 300 baud modem, which was...
Yeah. The high school had a 110 baud modem hooked up to a teletype, which was it was a box about this big on the wall beside the teletype, and you call a number, and yeah, it was, at the time it was, well, I don't know, it was cutting edge at the time, but it was pretty cool. And then to see the speed go up from 110 to 300 to 1200 to 2400 to 9600 was astonishing. 9600 was blazing. Anyway. Alrighty, well, we're supposed to have a second presenter, and I did get an email from Sergio at about 7:05 saying he's running late. He'll try and join as soon as he can. But unfortunately, he's not here. So we can hang out for another couple minutes. I don't know if anybody's got an interesting topic to discuss or a question to ask the group. But if not, I guess we can cut it short and we can hear Sergio's presentation in May. Anyway, thoughts? Anyone have questions? Comments? Thoughts about staying inside? Not much. Okay. Well, in that case, I guess we'll call it a night. I'm just going to go up here and do the end broadcast thing. Yes, end of broadcast.